Good morning, everyone. I'm Narsimhulu, Associate Professor, Department of Physics, St. Peter's Engineering College. Today, we are going to discuss about generation and detection of AM waves. Yeah, let us look into this switching modulator. A switching modulator is the way how to generate the AM waves. This is very basic fundamental mechanism how to generate the AM waves. It includes diodes and resistors and band pass filters. When we look into the diagram, here for the input of the circuit including this M of t and C of t. It means M of t, C of t means M of t is a message signal, C of t is a carrier signal, which are simultaneously connecting to the input circuitry. Here we have the diode. It is a non-linear device. RL is the load resistance and V2 of t is the output of the RL, and V2 of t is similar to the V1 of t. Means by this you can say that the slope between the V1 and V2 is equal to the 1. And bandpass filter, which is having input is V2 of t. Here V2 of t is consisting of the wanted components and unwanted components. The bandpass filter, which was having tuned to carrier frequency and rejecting the unwanted frequency components, accepts only wanted frequency components. This is explains you that one how the diode is going to be functionally work. Consider a semiconductor diode which was part of diagram used as a ideal switch, which is a carrier wave C of t and message signal M of t simultaneously which apply to the circuit diagram. You can understand V1 of t is equal to M of t plus C of t. Means M of t, C of t both are connecting to the input of the diagram simultaneously. So we are adding those two signals. So V2 of t is similar to the V1 of t. You can understand C of t is equal to AC cos 2 pi f ct and M of t is equal to AM sin 2 pi f mt, where mod of M of t less than AC means peak amplitude of the message signal always must and should less than AC. AC is the peak amplitude of the carrier signal. Output of the diode is going to be conduct when C of t is greater than 0. Okay, output of the diode is not going to be conduct when C of t is equal to less than 0. Means V2 of t is going to be depends upon the how the diode is going to be conducting. V2 of t is going to be equal to the V1 of t when C of t is a carrier signal having the amplitude of that signal is greater than 0. V2 of t is equal to 0 when C of t, the carrier amplitude signal is less than 0. The output of the diode varies between the 0 and 1 only. It is a rate, it is equal to the 1 by Fc. That is a carrier frequency. The diode is a non-linear device. It is having the non-linear behavior, can be replaced by assuming the weak modulating signal compared with the carrier wave. Thus, the output of the diode is approximately equal to the linear time varying operation. Mathematically, we can write that output of the diode V2 of t, which is going to be connecting to the input of the bandpass filter, equal to the V1 of t, Gp of t. Gp of t is make you to understand how the diode is going to be conducting. It is depends on the sum function, rectangular pulse train function. V2 of t is equal to M of t AC cos 2 pi f ct Gp of t. Gp of t is the rectangular pulse train with the period equal to the carrier time period, that is 1 by Fc, representing Gp of t in the Fourier series by using this equation. Okay, these are the first terms you can be considered like a important things, and remaining all are hard harmonic components. Substituting equation 4 and equation 3, corresponding you will have these many mathematical things are there. The required AM wave centered at Fc is obtained by passing V2 of t through an ideal band pass filter. Generally, AM wave having the centered FC. It means carrier frequency. Center frequency is the carrier frequency. Upper sideband frequency is the FC plus FM. Lower sideband frequency is FC minus FM. You want to get this required AM signal. For that, we have to design the bandpass filter with center frequency FC. So you have to be design that bandpass filter center frequency is FC and upper sideband frequency of the bandpass filter FC plus FM and lower sideband of the bandpass filter FC minus FM. Though the signal which is coming as a V2 of T for the input of the bandpass filter, okay, which is allowing in the given limit of bands only with the center frequency FC and cutoff frequencies are FC plus FM and FC minus FM. Then the bandwidth of the bandpass filter must and should is equal to the 2 omega hertz. Omega is nothing but bandwidth of the message signal or modulating frequency or highest frequency of the modulating frequency. Here you can observe output of the bandpass filter V2 dash of t is equal to 2 pi m of t cos 2 pi fct plus AC by 2 cos 2 pi fct. Just we are taking common AC by 2 cos 2 pi fct. The remaining term is inside the bracket 1 plus 2 into 2 divided by pi by AC m of t. There you are replacing this Ka with 4 by pi AC, that is amplitude sensitivity. Just you are rewriting the equation V2 of t is equal AC by 2 cos 2 pi fct into 1 plus Ka m of t. It looks like the standard AM equation. The standard AM equation written like S of t suffix AM is equal AC cos 2 pi fct into 1 plus Ka m of t. This is similarly looks like the standard equation. So you can say that this diagram can be used to generate the AM signals. Next topic, detection of AM waves. Envelope detector, which is going to be detect the envelope of the modulated signal. From there, it is going to be separate the envelope and which is going to be regenerating the actual what the message signal was transmitted. It consisting AM wave, that is S of t AM is equal to AC cos 2 pi fct into 1 plus Ka m of t. And we have the series resistance RS, have the nonlinear device diode, and having the capacitor and load resistor. You are taking voltage across the load resistor. Here, the function of capacitor, it is charging and discharging. When it is charging, when it is discharging, it is depends upon the diode conduction. When the diode is conducts, when the diode is not conducting, it depends upon the S of t AM, that is standard AM signal, whatever you are applying for this circuit diagram. Envelope detector is a simple and highly effective device used to demodulate AM wave. It consisting of diode and resistor capacitor filter, RC filter. Let us go to this how the operation of this diode. During the positive of cycle of the input signal, diode is forward biased and the capacitor charges up to the peak value of the input signal. When the input voltage falls below the value of the diode becomes reverse bias and capacitor C discharges slowly through the load resistor RL. You need to be understand the capacitor is going to be charging towards the peak value through the diode as well as RS. The capacitor is going to be discharged, okay, through the load resistor. When the capacitor is charging, when the capacitor is discharging, capacitor is going to be charging when diode is in non-condition. Capacitor is going to be discharging when diode is in off condition, that is reverse bias. The discharging process continues until the next positive of cycle when the input signal becomes greater than the voltage across the capacitor, the diode conducts again and the process is repeated. It means that discharging, once it is initiated, it goes on discharging, okay, until and unless, okay, the diode voltage is greater than the capacitor voltage. In the next positive cycle, the diode voltage will become more than the capacitor voltage. Now diode will become on condition. Now capacitor is again going to be charging. When diode voltage is lesser than the capacitor voltage, diode will become reverse bias, will become on condition. Then capacitor is going to be discharged through the resistor RL. Here, how the capacitor is going to be charged, how the capacitor is going to be discharged, how much time we have to be keep for the charging, how much time we have to be keep for the discharging, in terms of selection of the RC components. Which one is preferable? What are the conditions need to be satisfied to extract exactly what is the envelope of AM signal to generate modulating information? The capacitor charges through the diode and as well as RS when the diode is on. It discharges through the RL when diode is off. The capacitor having the time constant, that is RSC, should be very short. The time constant should be very short, mean it need to take time to charge towards the positive peak should be very small. The capacitor need to take the time to charge towards the peak value should be very small. The shorter time is required to the capacitor to charge towards the positive peak of the input signal. That's what RSC should be short. Here, how the RSC value is going to be defined? RSC should be short, mean what? It is greater than, RSC should be less than 1 by FC. 1 by FC is nothing but it is a time period of the carrier signal. Because carrier frequency is going to be impacting that one. How fast that amplitude of the carrier signal is changing. That's what we are taking, that period of the carrier signal, not period of the message signal. So we have taken the period of the carrier signal in terms of 1 by FC, so that the capacitor charges rapidly. It is try to get acquire the positive voltages or positive peak voltages or peak voltages very fastly. On the other hand, the discharging time constant ILC, we know that one. When diode is in reversed bias, the resistor is going to be discharging, sorry, capacitor is going to be discharging through the load resistor. But whatever we consider towards the charging by the capacitor to acquire the positive peak voltages or peak voltages, the time requirement should be very small. But while it is discharging the capacitor, the time required to be very large. Why? Because when you take that one, time requirement to discharge the capacitor is very large. So it is going to be discharged very slowly, okay, until and unless reaches to the particular value. Before that only, which is going to be having again positive peak value at the input side. So it is easy to trace out that one. What is the envelope? What is the envelope of the modulated signal? On the other hand, the discharging the time constant RLC should be long enough to ensure that the capacitor discharges slowly through the low resistance RL between the positive peak value of the carrier wave. So we have to be choose RLC should be lesser than 1 omega but greater than 1 by Fc, where omega is the maximum modulating frequency. Result is that capacitor voltage or detector output is very nearly the same of the envelope of AM wave. The detector output usually has a small ripple at the carrier frequency. This ripple is easily removed by using low pass filter. Now let us look at this one, envelope detector. This is, you can be observed, this is the discharging time. This is the charging time. As we discussed so far, the time taken to charge is very small. The time taken to discharge is very large. When it is very large, then what happens? Here, like you know that this is the time taken to discharge. When it is discharged, immediately next peak is coming here. So again, it is going to be charged. Because if you take that one, time taken to discharge is very slow. Means the envelope is looks like this. Again, you have to be go like this. Again, it is going to be consider like this. Again, you have to be go to consider like this. Again, you have to be go to consider this. This envelope, it's not exactly replica of the message signal. That's what we have to be choose the capacitor value and RS resistance, RL resistance according to the satisfying the condition to make it to charging of the capacitor is uh, should be take lesser time compared to the discharging of the capacitor. This is today